Hello everybody. In this video we're going to focus on linear programming. Linear programming is a way of optimization. So we're going to see how we're finding the maximum and minimum. We're going to determine the bounded and unbounded region. We're going to decide the feasible region, which is our solution set. And we're going to find the objective function and constraints. What is linear programming used for? Linear programming is used for obtaining the most optimal solution for a problem with given constraints. So we need an objective function and constraints. We can formulate our real-life problem into mathematical model, and using the linear programming we can solve it by optimization. Here the example of bounded region. So our solution set, which is feasible region, is enclosed by 4 vertices. So this closed area is called bounded region. If the area is not totally closed, it is partially bounded, so it is unbounded region. In this picture, as we go further down, we don't have limitation there. So we don't have minimum in this picture. Let's see example 1 on linear programming. Find the minimum and maximum value of 3x plus 4y. This is our objective function, and we were given 3 constraints. X is greater than or equal to 0, y is greater than or equal to 0, x plus y is less than or equal to 8. You can solve this problem either algebraically, graphically, or even using the matrices. Let's see how we can solve this problem algebraically and graphically first. This is our objective function, which is 3x plus 4y. And here are our constraints. We need to graph the constraints. So x is greater than or equal to 0 is the right side of the y-axis. And y is greater than or equal to 0 is the above the x-axis. So the intersection of these 2 constraints is the first quadrant here. So this is our xy plane. So this region is y is greater than or equal to 0 because it is above 0. And this region, right, is x is greater than or equal to 0, the right side of the xy plane, and the intersection together is the first quadrant. Now we are on the first quadrant. X plus y is less than or equal to 8 is this line. You can graph this line either solving for y is less than or equal to negative x plus 8, and you can graph it because y is less than or equal to, so below is the region. Or you can directly use the graphing utility. Another method is finding the x and y intercept. When x is equal to 0, we can find the y-intercept, and if we plug in 0 for x, it's going to be y is less than or equal to 8. And when y is equal to 0, then we can find the x-intercept, which will be x is less than or equal to 8. And the coordinate here, the point, will be 0, 8, and here will be 8, 0. As you can see in the picture, it confirms. So either graphing utility will give you this picture, giving these constraints, or algebraically you will do it by hand and find these vertices. So we have 3 vertices here, 0, 0 from these 2 constraints, 0, 8 and 8, 0 from the last constraint. And if you see the feasible region, it's going to be this triangle. Now we're going to find the min and max. So at 0, 0, our objective function is when we plug x 0 and when we plug in y 0. So 3 times 0 plus 4 times 0, which is 0. And at 0, 8, our objective function is 3 times 0 plus 4 times 8, which is 32. And our objective function at 8, 0 is equal to 3 times 8 plus 4 times 0, which is 24. So the minimum value numerically is the min. So this is our minimum and this is our maximum. So now we know the minimum and the maximum of the objective function. Let's see example 2. In example 2, we were given 5x plus 6y as our objective function, and we were given 4 constraints. X is greater than or equal to 0, y is greater than or equal to 0, x plus y is greater than or equal to 5, 3x plus 4y is greater than or equal to 18. Here, we start by graphing the constraints on the xy plane. If you use the graphing utility, you will see that this line here is x plus y is greater than or equal to 5. So this red line is our x plus y is greater than or equal to 5. You can manually draw it as well if you want. And this black line here is our 3x plus 4y is greater than or equal to 18. So this is our 3x plus 4y is greater than or equal to 18. And x is greater than or equal to 0 and y is greater than or equal to 0, so it is our first quadrant. So this is the region this is our feasible region, but it is unbounded. We have minimum, but we don't have maximum, because as we go further up, we still get some value for the objective function, and there is no limitation on up here. So here we can only find the minimum for this objective function. Let's find that. So we are going to plug in vertices into objective function. So at 0, 5, our objective function c is equal to 5 times 0 plus 6 times 5, which is 30. At 2, 3, our objective function is 5 times 2 plus 6 times 3, it is 28. And at 6, 0, our objective function c is 5 times 6 plus 6 times 0, which is 30. So our minimum is 28 at 2, 3. So this is the minimum point. Let's see our example 3. Two manufacturing plants make some kind of bicycle. The table gives the hours of general labor, machine time, and technical labor required to make one bicycle in each plant. For the two plants combined, the manufacturer can afford to use up to 4,000 hours of general labor, up to 1,500 hours of machine time, and up to 2,300 hours of technical labor per week. Plant A earns a profit of $60 per bicycle, and Plant B earns a profit of $50 per bicycle. How many bicycles per week should the manufacturer make in each plant to maximize the profit? So we need to find the objective function first. So let A and B represent the number of bicycles made in Plant A and Plant B respectively. So we know that bicycle A is $60 per bicycle. So our objective function will be 60A plus 50B. So this is the rate of bicycle A and this is the rate of bicycle B. Since we are aiming the maximum profit, so their addition, their sum will be our objective function. Now let's go ahead and write the constraints. So we know that 10 bicycle A plus 1 bicycle B is less than or equal to 4,000. This is the general labor. So this is general labor up to 4,000 hours. One bicycle A plus 3 bicycle B is less than or equal to 1,500. This is our machine time. And our 5 bicycle A plus 2 bicycle B is less than or equal to 2,300. And this is our technical labor limitation. And we know that the production cannot be negative, so A is greater than or equal to 0 and B is greater than or equal to 0 because the production cannot be negative. Here our 10 and 1 is obtained from the table here, because in the general labor we produce 10 bicycle A and 1 bicycle B, and using the machine time we produce 1 bicycle A, 3 bicycle B, and technical labor 5 to 2. Now we have constraints here as well. Now we are going to see how we are going to maximize. So you can directly graph these linear equations on graphing utility, or you can directly find the vertices and then plug vertices into the objective function. So if you graph them, this will be the graph you're going to obtain. And using the constraints, getting these vertices we obtained, we can directly plug in vertices into our objective function here and see which number has the highest value. So we have 0,500 at 0,500. Our objective function, which is 60A plus 50B, will be 60 times 0 plus 50 times 500, which is going to be 25,000. And at 300, 400, the second vertex here, we're going to obtain, if you plug in 300 on A and 400 on B, you're going to obtain 38K. And similarly, at 380, 200, you're going to obtain 32.8K. And at 0, 0, you're going to obtain 0. And at 400, 0, you're going to obtain 24K. So here, as you can see, our optimum maximum is at this vertex. So at 300, 400, this is our maximum profit. So that means that making 300 bicycles in plant A and making 400 bicycles in plant B will give us the maximum profit. Let's continue with practice problems. In problem 1, find the minimum and maximum of the function f equals to x plus y subject to these constraints. So this is our objective function, which is x plus y. This is our objective function. And these are our constraints. Since we're going to find minimum and maximum, we need to optimize this objective function. So our step 1 is to graph all constraints on xy plane. You can do it either manually or use the graphing utility. So I'm going to use the graphing utility for these constraints. So y is less than or equal to 0. So y is less than or equal to 0. So this part of the xy plane is scanned. And x is less than or equal to 0. So let's graph that as well. X is less than or equal to 0. So now quadrant 3 is our intersection. And finally, 6x plus 4y is less than or equal to negative 24. 6x plus 4y is less than or equal to negative 24. Okay, now we can see that this is our region. So our region is bounded by negative 4, 0 is one of our vertex, and 0, negative 6 is our another vertex. And this is unbounded, so there is no minimum because it is unbounded from the bottom part here. So let's go ahead and graph it. So our region looks like negative 4, 0 and 0, negative 6, and all this region down here. Now at negative 4, 0, our objective function f is equal to what? Our objective function x is equal to x plus y. So negative 4 plus 0 is negative 4. And at 0, negative 6, our objective function is negative 6 because 0 plus negative 6 is negative 6. So we don't have minimum because this is unbounded here. So it is n here. And our maximum is here because negative 4 is greater than negative 6. So our maximum is negative 4. Problem number 2. Given the system of inequalities below, determine the shape of the feasible region and find the vertices of the feasible region. Give the shape as triangle, quadrilateral, or unbounded. Okay, so we were given some constraints and we're going to determine the feasible region, the shape of the feasible region, and the vertices. We can manually do it and graph it on xy plane always, or we can use the utility for graphing and make it faster. And if you have more complicated constraints, you can even make augmented matrix and use Gauss elimination and solve for the variables and find the vertices. Now we're going to use the graphing utility. So our constraints are these. So let me graph them on graphing utility. Our first constraint is x plus y is less than or equal to 8. And our second constraint is 2x plus y is less than or equal to 10. Our next constraint is x plus 3y is greater than or equal to 11. and finally x is greater than or equal to 0, y is greater than or equal to 0. Okay, so our region, our intersection is this, bounded by 0, 8, 2, 6, 3.8, 2.4, and 0, 3.667. So this is our region. So we can extract these vertices, and our shape is the quadrilateral. Okay, our shape is something like this. And our vertices are 0, 8, 2, 6, 0, 11 over 3, or 3,667, and 3.8, 2.4. You can either write in fraction or decimal point. Either is correct. And the shape of our feasible region is quadrilateral. Problem number 3. Problem number 3 is similar to problem number 2. We were given some constraints. We're going to determine the shape of the feasible region, and we're going to find the vertices. So we're going to graph these constraints on the graphing utility rather than manually to save more time. So we were given x plus y is less than or equal to 7. And we were given 9x plus y is greater than or equal to 13. And finally, we were given x is greater than 0, y is greater than 0. So our feasible region is this triangle, because that's the intersection of all constraints. So our vertices are these. So 0.75, 6.25, 7, 0, and 1.444, 0 are our vertices. Let's go ahead and write that. So if we simulate, this is our triangle region, and our vertices were 0.75, 6.25, 1.444, 0, and 7, 0. And our feasible region is a triangle. And you can copy paste the vertices here. So that's going to be correct answer. And you don't need to write anything here, because instructions are like that. Problem number 4. Determine which of the regions A, B, C, or D in the figure above represents the graph of the given system of linear inequalities. So these linear inequalities are our constraints. We're going to graph it and see where it falls in the region A, B, or C and D. And we are going to determine whether it is bounded or unbounded. Linear programming problems can be solved manually by graphing using matrices, or you can even use more complicated software like MATLAB or Python if you have more complicated constraints. Now we're going to graph only. So our constraints are 3x minus 2y is greater than or equal to 0, and 2x plus 3y is less than or equal to 6. So this is our region. Our region is starting from the top of this triangle and going down unboundedly. So let's simulate it on our system. So it is like this, starting from here, the top, and all this region unboundedly. So region is unbounded, and the region is on this red area, which is B. Problem number 5. Graph the system of inequalities, tell whether the system is bounded or unbounded, and list each corner point. So these are our constraints. We're going to graph them and see whether it is bounded or unbounded. And we're going to decide the corners, which is vertices. So our constraints are x plus 3y is greater than or equal to 10. And we have y is greater than or equal to 2x. We have x is greater than or equal to 0. And finally we have y is greater than or equal to 0. So this is our region, this vertex and that vertex here, and it is unbounded from above, and these are our vertices. Let's go ahead and write down. So our region is unbounded, because it goes unlimited above, and our corners are 0, 10 over 3, or you can write 3.333, 1.429, 2.857. Problem number 6. The above is the graph of a system of linear inequality constraints. The corner points of the graph are 5, 19, 14, 20, 15, 13, 9, 3. Find the maximum value of z equals to 2x plus 5y over the graph. So our objective function is z is equal to 2x plus 5y, and we were given the vertices, which are 5, 19, 14, 20, 15, 13, and 9, 3. Since we're going to find the maximum, we need to plug in corner values into objective function. So at this corner, what is the value of the objective function? That's what we are concerned. So here our x value is 5, so 2 times 5, plus our y value is 19, so this calculation gives us 105. Here 2 times 14 plus 5 times 20, and this computation gives us 128, and 2 times 15 plus 5 times 13 is equal to 95. Finally 2 times 9 plus 5 times 3 is equal to 33. Since this is the highest value, so at this corner this is our maximum and this is our minimum. So the maximum value of z is 128 at the corner point of 14, 20 here. Problem number 7. The above is the graph of a system of linear inequality constraints. The graph is unbounded and its corner points are 0, 28, 14, 0, and 2, 1. So what's the minimum value of the objective function? Again, we were given the objective function z, which is 5x plus y, and we were given the corners. We have 0, 28 is one of the vertices, 14, 0, and 2, 1. So we're going to compute the value of objective function at this corner. So our x value here is 0 and our y value is 28. 5 times 0 plus 28 is equal to 28. And here 5 times 14 plus 0 is equal to 70. And here 5 times 2 plus 1 is 11. Since we're looking for the minimum value, so the lowest value here is 11 at this corner. So the minimum value is 11 at the corner of 2, 1. Problem number 8. Blink Appliances plans to order microwaves and stoves. Each microwave requires 1.5 hours to unpack and set up in the storeroom, and each stove requires 3 hours. The storeroom space is limited to 66 items. The budget of the store allows only 150 hours of employee time for unpacking and setup. Microwaves yields a profit of $97 each, and stoves yields a profit of $152 each. How many of each should the store order to maximize the profit? Here, we're going to find the objective function and constraints first. We know that it requires 1.5 hours for each microwave and 3 hours for each stove to unpack, and we are limited with 150 employee hours. And we know that our space is allowing only 66 items, which is the combination of microwave and stoves cannot exceed 66 items. And m is greater than or equal to 0 because we can't have negative production, and s is greater than or equal to 0. These are our constraints. Our objective function is our profit function, which is the rate of microwave, which is $97 m plus $152 for stove. So we're going to solve these constraints and find the vertices, corners, and plug into objective function and see which one gives us the maximum value. So let's directly graph this. So we have 1.5, let x be the microwaves, plus 3y, let y be the stoves, and that is less than or equal to 150. And x plus y is less than or equal to 66. We have x is greater than or equal to 0, and y is greater than or equal to 0. So this is our feasible region. Our vertices are already clear there. We have quadrilateral here, and these are our vertices. Let's copy paste this here and work on the profit function. So if we plug in these corners into profit function, we can see the maximum. So 97 times 0 plus 152 times 50 is this corner, and the computation here gives us $7,600. This corner is giving us 97 times 32 plus 152 times 34 gives us $8,272. And this corner, if we plug in 97 times 66 plus 152 times 0, gives us $6,402. So as we can see here, this is our maximum profit. So $8,272 is our maximum profit, and the point is 32,34, which is the number of microwaves and the number of the stoves. Problem number 10. Maximize the function p equals to 2x minus 5y subject to these constraints. We're going to determine the corner points of the feasible set, and we're going to compute the maximum value. Let's start with graphing the constraints. So we were given x is greater than or equal to 0. We have y is greater than or equal to 0. We have 6x plus 5y is less than or equal to 30. And finally we have 9x plus 2y is greater than or equal to 18. Now this is our feasible region, this triangle, and let's copy paste that. And compute the maximum value. First of all, we know our vertices already, so we can write that down. So the corners of the feasible set is 0.909, comma 4.909, comma 2, 0, comma 5, 0. Now we know that our objective function p is equal to 2x minus 5y. And at this point, it is 2 times 0.909 minus 5 times 4.909, and this value is equal to negative 22.727. At this point, we have 2 times 2 minus 5 times 0, because x value here is 2 and y value is 0. And this equals to 4, and at this point we have 2 times 5 minus 5 times 0, which is 10. Since we're looking for the maximum value, we're going to pick up the highest value, which is 10. So the maximum value is 10 at the corner of 5, 0. Problem number 9. Graph the following system of linear inequalities and determine the corner points and find a point that is in the feasible set of the system. So we're going to graph these constraints given, which were x is greater than or equal to 0, y is greater than or equal to 0. We have 3x plus 8y is greater than or equal to 12, and finally we have 3x is greater than or equal to y. So our feasible region is this region, starting from this vertex to this vertex, and all this feasible region is our region. Let's copy paste this and determine it. So our feasible region is starting from here, this vertex, here, and here. Because this area is x is greater than or equal to 0, y is greater than or equal to 0, 3x plus 8y is greater than equal to 12, and at the same time 3x is greater than or equal to y. And these are the corners. Let's write that 0.444, 1.333, 4, 0, and you can pick up any point in this feasible region. I would like to pick up 2, 2, because 2, 2 is in the feasible region. Problem number 10. Maximize the function p equals to 2x minus 5y subject to these constraints. We're going to determine the corner points of the feasible set, and we're going to compute the maximum value. Let's start with graphing the constraints. So we were given x is greater than or equal to 0. We have y is greater than or equal to 0. We have 6x plus 5y is less than or equal to 30. And finally we have 9x plus 2y is greater than or equal to 18. Now this is our feasible region, this triangle, and let's copy paste that. And compute the maximum value. First of all, we know our vertices already, so we can write that down. So the corners of the feasible set is 0.909, comma 4.909, comma 2, 0, comma 5, 0. Now we know that our objective function p is equal to 2x minus 5y, and at this point it is 2 times 0.909 minus 5 times 4.909, and this value is equal to negative 22.727. At this point we have 2 times 2 minus 5 times 0, because x value here is 2 and y value is 0, and this equals to 4. And at this point we have 2 times 5 minus 5 times 0, which is 10. Since we are looking for the maximum value, we're going to pick up the highest value, which is 10. So the maximum value is 10 at the corner of 5, 0. Problem number 11. Write a formula for the inequality graphed above in the form ax plus by, inequality sign, and some constant c. So for this, we're going to enlarge the graph, and we're going to find the equation of this line and graph that inequality. So we're going to pick up 2 points on this line. So 1, 0 is the point on this line, and 0, 4 is another point on this line. Since we have 2 points on this line, we can find the slope. Slope is y2 minus y1, which is delta y, over x2 minus x1, which is delta x. So here, this is our x1, y1, x2, y2. So 0 minus 4 over 1 minus 0 is negative 4 over 1, which is negative 4. So negative 4 is our slope. You could also count here on the graph, rise over run, 1, 2, 3, 4 units down, which is negative 4, and 1 units right, which is positive 1, and rise over run would be negative 4 over 1. That would be our slope, m. We can plug in the slope and one of the points into point slope form, which is y minus y1 equals to m times x minus x1. Or you could also use y equals to mx plus b, which is the slope-intercept form. But we're going to use standard form, which is ax plus by equals to some constant c. First we're going to plug in one of these forms and then convert it into standard form of the linear equations. We know that our y1, let's pick up this point 1, 0. Here this is our x1, this is our y1. So our y1 is 0, y minus 0 equals to m is negative 4, we found. X minus x1 is 1. If you simplify here, y is, we're going to use greater than or equal to sign because this is a solid line, and negative 4x plus 4. Now we're going to convert this into standard form. We're going to add 4x on both sides. So we're going to obtain 4x plus y is greater than or equal to 4. So this is our final answer. So 4x plus y is greater than or equal to 4 will give us this region here. Problem number 12. Suppose you walk for W hours at 2 miles per hour and then drive a car for D hours at 60 miles per hour, covering a total distance of 60 miles. Write a constraint equation that relates the time spent walking and driving to the total distance covered. So let's continue with part A. First of all, we need to know that distance equals the rate times time. So here our total distance t is equal to walking plus driving. So here we're going to write walk equation and we're going to write here drive equation. So the distance from walking is 2 times w because 2 is the rate of walking, 2 miles per hour, and w is the number of the hours. For the drive equation, we're going to write 60d. 60 is the rate of the driving, 60 miles per hour, and d is the total hours. And here our t is 60. It is given in the problem because total distance is 60 miles. So our constraint equation will be 2w plus 60d is equal to 60. Now, if you only walk and do not drive, how much time do you spend walking? So here we are not driving, so d is 0, and our total distance is 60 miles already, and 2w. If you solve for w here, w will be 30, so you have to walk 30 hours. If you only drive, this time walking rate will be 0, so total distance t will be equal to 60d, and if you solve for d, it's going to be 1. So you're going to drive 1 hour only. Find the solution to your equation in part A that has spent some time driving and some time walking. So the graph of this scenario looks like D here, the blue line, and x coordinate of any point on this line refers to walking hour, and any coordinate y on this line refers to driving. So x hour walk and y hour drive. So part D is technically asking pick a point on this line. So we're going to pick a point on this line, which is the combination of walk and drive. Let's use our graphing utility and graph it. So 2x plus 60y equals to 60 is the graph of the scenario. So you need to pick a point. So any point you pick on this line is correct. 2.99, 0.9 is correct. So I would like to pick 2.99, 0.9 hours. And the check is this. Check is 2 times 2.99 plus 60 times 0.9 has to be equal to 60. So that confirms that this is a point on this line. Now, on a piece of paper, sketch a graph your equation in part A. So the equation will look like this. So this is 0,60, and it's going to be decreasing line, and any point on this line refers to walking plus driving, walk hours and drive hours. So here the answer is D. That blue line looks like our sketch.